Hello, everyone. Tonight, we're going to travel through the universe by following one idea: gravity. Not the gentle gravity that keeps your feet on the ground or the moon in the sky, but gravity at its most extreme. Gravity so concentrated that space and time bend inward, and a region forms from which light cannot return. A black hole. Black holes can sound like monsters in the dark, but in science, they're more like landmarks. Natural consequences of matter, energy, and space-time interacting under very specific conditions. And there isn't just one kind. There are families of black holes, grouped by mass, by origin, by environment, and sometimes by theories that reach beyond what we can currently test. So tonight, we'll take a slow, calming tour of the main black hole types people talk about when they want the full map. Stellar mass black holes, intermediate mass black holes, supermassive black holes, primordial black holes, binary black holes, and quantum black holes, which live more in the realm of theoretical physics than confirmed astronomy. Along the way, we'll gently clear up a few common confusions. A black hole is not a vacuum cleaner. It doesn't suck more than anything else with the same mass. From far away, its gravity behaves like any other object of equal mass. What makes it special is not its personality, it's its compactness, its density, the way its mass is packed into a small enough region that the escape speed exceeds the speed of light. And because this is a sleep-friendly story, we'll keep the tone soft. Think of this as a night walk through a museum that stays open after hours. The exhibits are dark, the lights are low, and every room is devoted to a different way the universe can fold itself inward. Take a slow breath. Let your shoulders drop. And let's begin with the simplest question. What makes a black hole a black hole? A black hole is defined by a boundary called the event horizon. The event horizon is not a physical surface like a planet's crust. It's a point of no return in space-time. Cross it, and every future path points deeper inward. Even light, traveling at the maximum speed the universe allows, cannot climb back out. Outside the horizon, you can orbit, escape, fall in, or pass by. Inside the horizon, out is no longer a direction you can choose. That's the core idea. Everything else, the spinning, the jets, the glowing disks of hot gas, those are add-ons created by the black hole's environment. A black hole itself, in the simplest description, can be remarkably simple. In general relativity, an idealized black hole is characterized by mass, spin, and electric charge. In real astrophysics, charge is usually negligible because the surrounding plasma neutralizes it quickly. So, most real black holes are described mainly by mass and spin. And mass is the key for tonight, because mass is what sets the scale. Mass decides how large the horizon is, how strong tidal forces are near the horizon, how long things take to orbit, how the black hole interacts with stars and gas. So when we say types of black holes, we often mean mass classes, but we also mean origin stories, because a black hole's mass is also a clue to how it formed. Let's step into the first major room: stellar mass black holes, the aftermath of massive stars. Stellar mass black holes are the ones formed from single stars. They are the classic black holes of astronomy, though even these were once speculative. A massive star lives fast and dies hard. For millions of years, it burns fuel in its core, fusing lighter elements into heavier ones. Fusion releases energy that pushes outward, supporting the star against gravity. But eventually, the star runs out of fuel it can fuse efficiently. When the outward pressure weakens, gravity takes over. The core collapses. Depending on the star's mass and internal conditions, the collapse can produce a neutron star or a black hole. A stellar mass black hole typically has a mass of a few times the Sun's mass, up to tens of solar masses. In recent years, gravitational wave detections have shown black holes with masses larger than many astronomers once expected from standard stellar evolution, like 20, 30, even more solar masses in merging binaries. That doesn't break physics. It points to the diversity of stellar environments. Metallicity matters. A star with fewer heavy elements tends to lose less mass through stellar winds. It can die with a heavier core. Heavier core means a heavier black hole. So, stellar mass black holes are not all identical. They come from different kinds of massive stars in different chemical neighborhoods of the universe. How do we find them? Sometimes by their gravitational influence on a companion star in a binary system. A visible star orbits something invisible. The orbit reveals a mass too large for a neutron star. Sometimes by the X-rays produced when the black hole pulls gas from a companion, forming an accretion disk that heats up as it spirals inward. Sometimes by gravitational waves, when two black holes merge and convert a few solar masses of energy into ripples in space-time. Stellar mass black holes are common compared to the bigger types. They are the universe's routine outcome for the most massive stars. Not everyday in a human sense, but common in a cosmic sense. They are the embers left behind when a star's nuclear fire goes out. The mass gap and why stellar remnants get complicated. If you listen to black hole science for a while, you may hear about mass gaps. One gap is between the most massive neutron stars and the least massive black holes. Another is the so-called pair instability gap, where certain very massive stars may explode in a way that leaves no black hole remnant in a certain mass range, depending on details of stellar physics. These gaps are not perfectly settled because nature is messy and our samples are still limited. But the existence of gaps, edges, and exceptions matters for one reason. It hints that black hole populations are not just a smooth continuum. They reflect specific formation channels. Different physics creates different remnants. So even within stellar mass black holes, there is a taxonomy. Black holes from isolated single stars. Black holes from binary evolution and mass transfer. Black holes formed after failed supernovae, where the star collapses with little outward explosion. Black holes formed in dense star clusters, where encounters can swap companions and build unusual pairs. Stellar mass black holes are the doorway into the larger zoo, because once you accept that black holes exist, the next question arrives naturally. If stars can make black holes of 10 solar masses, what makes black holes of 1,000, or 1,000,000, or 1,000,000,000? For that, we step into the next room. Intermediate mass black holes, the missing link class. Intermediate mass black holes are, in a way, the most mysterious major class. They are defined roughly as black holes in the range between stellar mass and supermassive. You'll see slightly different boundaries depending on the source, but a common idea is intermediate mass black holes might be from about 100 to 100,000 solar masses. These are too massive to form from a single star in the straightforward way, and too small to be the central engines of large galaxies, like the supermassive black holes we'll meet soon. For a long time, intermediate mass black holes were more of a prediction than a confirmed population. Scientists suspected they should exist, but proving it is hard. Why? Because a black hole is easiest to detect when it's either very massive or actively feeding. A quiet black hole, floating in space and not accreting, is almost invisible. Intermediate mass black holes might live in environments that don't always supply them with gas, or they might be rare, or both. Where might they hide? One plausible home is the center of a dense star cluster. Globular clusters, for example, contain hundreds of thousands to millions of stars packed into a relatively small volume. The cores of such clusters are gravitationally busy places. Stars interact. Binaries form and break. Objects sink toward the center through mass segregation. In some scenarios, repeated mergers of stellar mass black holes in the cluster core could build up a larger black hole over time. Another plausible home is the center of dwarf galaxies. Small galaxies may host central black holes that are not yet supermassive. They could be in the intermediate range. Finding them helps answer a bigger question. How did supermassive black holes get so big, so early in the universe? Intermediate mass black holes could be seeds that grew, or they could be an entirely separate population formed by different processes. Observationally, there are candidate intermediate mass black holes. Some ultra-luminous X-ray sources have been interpreted as possible IMBHs, though many can also be explained by stellar mass black holes accreting at high rates or with beaming effects. Some dynamical measurements of star motions in clusters suggest central dark masses, but interpreting those data can be challenging. Some gravitational wave events may hint at black holes in the intermediate range, including merger remnants that land there. The current honest picture is this: intermediate mass black holes are strongly motivated, and there is accumulating evidence and promising candidates, but the population is not as cleanly established as stellar mass and supermassive black holes. And that uncertainty is not failure, it is the frontier, a quiet region of the map labeled not with dragons, but with careful error bars. Why intermediate mass black holes matter beyond curiosity. Intermediate mass black holes are not just a missing shelf in a cosmic catalog. They connect two major scales of structure in the universe. They are a bridge between stars and galaxies. If IMBHs exist in large numbers, they could influence the evolution of star clusters, heating them dynamically and shaping their core structure. They could also merge and contribute to the growth of supermassive black holes. They could produce distinctive gravitational wave signals, especially if an IMBH merges with a stellar mass black hole, creating an intermediate mass ratio in spiral. And if IMBHs exist as seeds in early galaxies, they help explain how supermassive black holes reached masses of 1 billion suns less than 1 billion years after the Big Bang. That early growth problem is one of the great puzzles of modern astrophysics. So whenever Webb, X-ray observatories, and gravitational wave detectors push this field forward, they are not merely counting black holes. They are refining our story of how structure formed in the universe. Now, from the missing link class, we move to the giants. Supermassive black holes, the quiet titans in galaxy centers. Supermassive black holes are the largest well-established black holes in the universe. They live in the centers of galaxies, including our own Milky Way. Their masses range from millions to billions of solar masses. Some of the most extreme known examples may reach tens of billions of solar masses, though measuring the upper end has its own challenges. A supermassive black hole is so massive that paradoxically, the tidal forces at the event horizon can be less violent than those around a stellar mass black hole. Tidal forces scale with the gradient of gravity. For a given mass, the horizon radius increases, and the curvature at the horizon can be gentler. This leads to a strange truth. A very large black hole can be, at the horizon, a calmer place in terms of spaghettification than a smaller one. It's still a black hole, still a point of no return. But the immediate tidal stretching near the horizon can be less severe. Supermassive black holes are detected in several ways. By watching stars orbit an invisible mass at the galactic center. This is how the Milky Way's central black hole, Sagittarius A star, was measured. By observing the bright accretion disks and jets of active galactic nuclei, where the black hole is feeding on gas and shining across the electromagnetic spectrum. By detecting the motion of gas in the central regions of galaxies, by imaging the shadow-like silhouette of the black hole's horizon-scale environment, as the Event Horizon Telescope did for the black hole in M87, and later for Sagittarius A star. Though these images are not Webb images, they are radio interferometry. Supermassive black holes are not merely objects. They are engines. When they feed, they can outshine entire galaxies. Quasars are powered by accretion onto supermassive black holes, and their feedback radiation, winds, jets can heat and expel gas, regulating star formation in the host galaxy. This is one reason supermassive black holes are so central to cosmology. They are not passive occupants of galaxy centers. They are part of galaxy evolution. And yet, there is a deep mystery here. How did they form? How did they get so big? The universe had supermassive black holes very early. We see quasars at high redshift, when the universe was less than 1 billion years old, hosting black holes of 1 billion solar masses. Growing a black hole that large in that time is difficult, unless you start with a large seed or you allow very efficient accretion, or you merge many black holes quickly, or you use some combination. This is where intermediate mass black holes, direct collapse black holes, and primordial black holes sometimes enter the conversation. The story of black holes is also the story of how the early universe built monsters fast. Active versus quiet. The difference between a sleeping giant and a blazing quasar. Not all supermassive black holes are active. Many are quiet, like the Milky Way's central black hole, which is faint compared to a quasar. A supermassive black hole can exist in a low accretion state, feeding only on sparse gas, producing occasional flares. The difference between quiet and active is mostly about supply. Does gas reach the center? Is it driven inward by galaxy interactions, bars, or other dynamical processes? Is there enough cold material to feed a bright disk? When a supermassive black hole is active, it becomes easier to detect and study. When it is quiet, it can still be inferred by the gravitational effects on nearby stars and gas, but it can be less dramatic to observe. In a calm way, you might think of this as the difference between a lighthouse and a dark tower. The tower is still there, massive and real, whether or not it is shining. Now, we've covered 3 mass classes: stellar mass, intermediate mass, supermassive. These are the mainstream categories. But the universe may have other kinds, defined not only by mass, but by origin. And one of the most fascinating is the idea that some black holes might not come from stars at all. They might come from the early universe itself. Primordial black holes, hypothetical relics from the early universe. Primordial black holes are black holes that, if they exist, formed not from collapsing stars, but from density fluctuations in the early universe. In the earliest moments after the Big Bang, the universe was hot, dense, and expanding. Small variations in density existed. Under certain conditions, if a region was dense enough, it could collapse directly into a black hole. That would produce a black hole long before stars and galaxies formed. Primordial black holes, often abbreviated PBHs, are hypothetical. They have not been confirmed. But they are scientifically interesting because they connect cosmology, particle physics, and astrophysics. They could, in principle, span a wide range of masses. Some could be tiny, even microscopic in astrophysical terms. Some could be asteroid mass. Some could be stellar mass. Some could be larger, though producing extremely massive PBHs requires specific conditions. One reason PBHs attract attention is dark matter. Dark matter is a major component of the universe's mass. We infer it from gravity, galaxy rotation curves, gravitational lensing, cosmic microwave background structure, and more. But we do not yet know what dark matter is made of. PBHs are one candidate, but constraints are strong. If PBHs make up all of dark matter, they must fit within a narrow set of allowed masses and abundances that do not contradict observations like microlensing surveys, cosmic background limits, and gravitational wave event rates. So PBHs are not a simple answer. They are a carefully constrained possibility. Another reason PBHs matter is that they could provide early seeds. If PBHs of, say, tens or hundreds of solar masses existed early, they could help grow supermassive black holes by providing a head start, easing the early growth problem. But again, this must be consistent with observations. In science, PBHs are not mystical. They are a hypothesis, a lever we can test, a possibility that can be squeezed by data. And in recent years, as gravitational wave astronomy has expanded, some people have asked whether certain black hole merger events could involve primordial black holes. The current reality is that standard stellar evolution can explain many observed black hole mergers, but the PBH idea remains a topic of research. It's a bit like hearing a distant sound in a forest at night. It might be wind. It might be an animal. You don't claim certainty. You gather more evidence. You map the possibilities. That is where primordial black holes live right now, on the map of possibilities. Hawking radiation and the fate of very small black holes. When discussing primordial black holes, it's natural to mention Hawking radiation. In quantum field theory on curved spacetime, black holes are predicted to emit radiation. This is not because something escapes from inside the horizon in the classical sense, but because of quantum effects near the horizon. The result is that black holes can slowly lose mass, very, very slowly for astrophysical black holes, but potentially quickly for extremely small black holes. The smaller the black hole, the hotter it is in the Hawking picture, and the faster it evaporates. For stellar mass and supermassive black holes, the evaporation time is vastly longer than the current age of the universe. So Hawking evaporation is negligible for them. But for tiny primordial black holes, if they existed, Hawking radiation could have caused them to evaporate by now. This means there are constraints. If PBHs were too small, they wouldn't survive to the present day. If they were in certain mass ranges, their evaporation might produce detectable signatures, like gamma rays, which we can search for. So even though Hawking radiation has not been observed directly from black holes, it shapes how scientists think about the allowable mass range for primordial black holes that could still exist. This is the gentle pattern of science again. A theory suggests a phenomenon. Observations constrain it. Theories survive not by being dramatic, but by being consistent. Now, we've met black holes by mass and by origin. Next, we meet a type defined by companionship. Because in the universe, black holes often come in pairs. Binary black holes. When two black holes orbit each other, a binary black hole is not a different species of black hole. It is a system. Two black holes bound together by gravity, orbiting a shared center of mass. But binary black holes deserve their own place in the catalog because they are central to modern observational breakthroughs. Binary black holes are the primary sources for the gravitational waves detected by LIGO, Virgo, and CAGRA. When two black holes orbit each other, they emit gravitational radiation. This carries energy away. The orbit shrinks. The black holes spiral inward. The frequency and amplitude of the gravitational waves increase as the orbit tightens. Finally, they merge, producing a single more massive black hole and releasing a burst of gravitational wave energy. This is one of the most spectacular events in the universe, but it is also, in a quiet way, clean. The gravitational wave signal is described with remarkable precision by general relativity. It is a test of gravity in the strong field regime. Binary black holes can form through multiple channels. One channel is isolated binary evolution. Two massive stars are born together as a binary. They evolve. They expand. They exchange mass. They might pass through a common envelope phase where one star's outer layers engulf the pair, shrinking the orbit. They explode as supernovae or collapse directly. If the system survives, it can become a binary black hole. Another channel is dynamical formation in dense environments. In globular clusters or nuclear star clusters, many compact objects interact. Three-body encounters can form binaries. Binaries can harden through interactions. Black holes can swap partners. Eventually, a tight black hole binary can form and merge. There is also the possibility of black hole binaries in the disks of active galactic nuclei, where gas dynamics can help bring black holes together. Each formation channel leaves statistical fingerprints in the population: mass distributions, spin orientations, merger rates, eccentricities. So, binary black holes are not just events. They are probes. They tell us about stellar evolution, cluster dynamics, galaxy centers, and the history of star formation. In the sleep story mood, you can imagine binary black holes as slow dancers. For a long time, they orbit quietly. They lose energy in a way that is imperceptible until the final moments. And then, suddenly, in the last seconds, the dance accelerates into a final embrace that shakes space-time itself. Not loud in air, but loud in geometry. Loud in the shape of distance. And from that signal, we learn binary systems beyond black hole. While we focus on black hole binaries, there are other close relatives. Black hole neutron star binaries. Neutron star, binaries, black hole star binaries, where the star is not compact yet and can feed the black hole. These systems matter because they show different astrophysical behavior. Black hole star systems can be bright in X-rays. Neutron star mergers can produce electromagnetic counterparts like kilonovae. Black hole neutron star mergers sometimes produce light, sometimes not, depending on whether the neutron star is tidally disrupted outside the horizon. But black hole mergers are especially clean gravitational wave sources, often with little or no light. This is why gravitational wave astronomy was, in a sense, born in the dark, listening rather than seeing. Now, we've covered systems and origins, and we've covered masses. The next type is one you asked for explicitly, and it needs a careful tone, because quantum black holes are not currently confirmed objects the way stellar mass black holes are. They belong to the borderland where physics tries to unify the very large with the very small. So we'll step into that room quietly. Quantum black holes, theoretical objects near the Planck scale. When people say quantum black hole, they usually mean one of a few related ideas. A black hole so small that quantum effects dominate. A black hole whose mass is near the Planck mass, roughly 2.1810 minus 8 kg, 2.18 times 10, number 8 kg, which is tiny by everyday standards, about the mass of a grain of dust, yet enormous by particle physics standards. Or a black hole that forms in high-energy particle collisions in certain speculative theories involving extra dimensions. Or a black hole-like object that requires quantum gravity to describe properly, because classical general relativity predicts a singularity, and quantum physics suggests that the singularity description must be incomplete. In all of these cases, the key point is the same. We do not currently have a complete, experimentally verified theory of quantum gravity. We have strong frameworks and candidates: string theory, loop quantum gravity, effective field theory approaches, and others, but no single confirmed unified theory with direct experimental proof in the regime where quantum gravity effects are unavoidable. So, quantum black holes remain hypothetical. They are a way of labeling the idea that black holes and quantum physics must meet, and when they do, the story changes. A quantum black hole might evaporate quickly through Hawking radiation. It might not have a classical horizon in the same way. Some theories suggest horizon-scale quantum structure. Some propose remnants. Some propose that information is preserved in subtle correlations in radiation. These questions connect to the black hole information problem: how to reconcile black hole evaporation with quantum mechanics, which generally preserves information. From the standpoint of astronomy, quantum black holes are not the kind of objects we can point a telescope at today. If tiny black holes were produced in particle collisions, they would be extremely short-lived. And experiments like the Large Hadron Collider have not found evidence supporting black hole production, placing constraints on certain models. That doesn't mean the idea is dead. It means the universe has not offered confirmation yet. So why include quantum black holes in a catalog? Because black holes are where our current theories are pushed hardest. They are places where gravity is strong, and where quantum effects at horizons raise deep questions. Even if quantum black holes are not confirmed astrophysical objects, they are a vital part of the intellectual landscape. They are black holes as theoretical laboratories. In a calm bedtime framing, you can think of them as the smallest possible knots in space-time, imagined by theories that are still being tested, still being built, still being argued over in chalk dust and late-night papers. Now, there is one more term you included: ilkel, meaning primordial. We've covered primordial black holes as early universe relics. But the taxonomy can go further, because black holes can also be categorized by how they rotate, how they feed, and how they behave in their environments. These are not separate species so much as modes. Still, they help complete the picture. Rotating, charged, and the personality traits black holes can have. In the simplest theoretical descriptions, a non-rotating, uncharged black hole is called a Schwarzschild black hole. A rotating black hole is called a Kerr black hole. A charged, non-rotating black hole is a Reissner-Nordstrom black hole. A charged, rotating black hole is a Kerr-Newman black hole. In real astrophysics, black holes are expected to have very little net electric charge because surrounding plasma cancels it. But spin is extremely important. Black holes can spin rapidly, and spin affects the structure of space-time outside the horizon. It creates an ergosphere, a region where space-time is dragged around with the black hole's rotation. Spin can influence how accretion disks behave and how jets are launched. Many of the most spectacular black hole phenomena, relativistic jets, extending thousands or millions of light years, are thought to be connected to magnetic fields and rotation. So while rotating black hole isn't a separate mass class, it is a key subtype in behavior. Most real black holes are likely Kerr-like, rotating, mostly neutral. This matters for sleep narration because it replaces a vague fear with a clear image. A black hole is not a magical mouth. It is a rotating region of curved spacetime, a dynamical object that interacts with plasma, magnetic fields, and radiation in specific, understandable ways. And understanding is often calming. Feeding black holes, accretion disks, jets, and the light that comes from darkness. A black hole itself emits no light in the classical sense, but black holes can be surrounded by luminous matter. If gas falls toward a black hole, it usually doesn't plunge straight in. It has angular momentum. It forms an accretion disk. Friction, turbulence, and magnetic processes heat the disk. The inner disk can become extremely hot and bright. For stellar mass black holes, the hottest inner disks shine in X-rays. For supermassive black holes, the disk can shine in ultraviolet and optical, and the surrounding dust can re-radiate in infrared. In active galaxies, jets can launch from near the black hole, powered by magnetic fields and rotation. These jets can carry energy far into the galaxy and beyond, shaping the surrounding medium. So when people say black holes are invisible, the correct calming reply is, black holes are often surrounded by some of the brightest environments in the universe. We see not the whole, but the consequences. We see matter on the edge of falling forever. We see gravitational influence. We see energy release from accretion. We see the geometry imprinted in radiation. This is how black holes became a mature observational science rather than a mathematical curiosity. Now, to be thorough, there are a couple of other black hole categories that appear in discussions, and even if you didn't list them explicitly, they help complete all types in a practical sense. They also help clarify what we mean by type. Micro black holes and mini black holes, size versus origin. Sometimes people talk about micro black holes or mini black holes. These terms can refer to different things depending on context. In cosmology, a micro black hole might mean a small primordial black hole, perhaps asteroid mass or smaller, formed in the early universe. In particle physics, a micro black hole might mean a hypothetical black hole produced in a high-energy collision, possibly in theories with extra dimensions. In either case, the key point is that micro is about mass and scale, not necessarily origin. And for very small black holes, Hawking radiation becomes important. They would not behave like astrophysical black holes we imagine swallowing stars. They might evaporate rapidly. They might exist briefly. They might produce bursts of high-energy particles. These possibilities are tightly constrained and not confirmed, but including them in the map helps avoid confusion. When someone says small black hole, they might mean stellar mass, or they might mean primordial micro-black hole. The universe uses the same underlying concept, but the stories differ. So, in our Museum of Black Holes, micro and mini are labels that point to the small-scale wings, where theory meets constraint. Seed black holes and direct collapse black holes, how giants might begin. Another term you may hear is seed black hole. A seed black hole is not a separate physics object. It is a role in cosmic history. A seed is a black hole that forms early and then grows. Seeds might be stellar mass remnants of the first stars, called population 3 stars, which formed from very low metallicity gas in the early universe. Those first stars may have been very massive, and their remnants could have been heavier than typical stellar black holes today. Seeds might also form through direct collapse. In some scenarios, under special conditions, large clouds of gas can collapse directly into a massive black hole without fragmenting into many stars first. That could produce a black hole of tens of thousands or even more solar masses early on, providing a head start towards supermassive scales. These direct collapse black holes are an active research topic. They are difficult to confirm because they would exist at very high redshift and their light would be entangled with their host environment. But Webb and other observatories are part of the search, looking for candidate signatures of massive black hole formation in early galaxies. So when you ask for all black hole types, it's useful to include these formation channels because they connect directly to the biggest questions about supermassive black holes. How do they grow so fast? Did they start small and accrete efficiently? Did they start big through direct collapse? Did mergers contribute significantly? Did primordial black holes play a role? Science currently answers, we're narrowing it down, not with one dramatic revelation, but with better constraints. A calm, connected taxonomy, the black hole map in one view. Before we continue, it can help to hold the whole map in your mind, gently, without trying to memorize it. There are black holes categorized by mass: stellar mass, intermediate mass, supermassive. There are black holes categorized by origin: stellar collapse black holes, possible direct collapse seeds, possible primordial black holes. There are black holes categorized by configuration: isolated black holes, binary black holes, black hole systems with stars or neutron stars. There are black holes categorized by theoretical regime: classical general relativity black holes, which describe astrophysical black holes very well; quantum black holes, which are hypothetical objects requiring quantum gravity to describe fully; And there are black holes categorized by behavior. Quiescent black holes that are not actively accreting. Active black holes powering X-ray binaries, quasars, and jets. All of these categories overlap. A supermassive black hole can be active or quiet. A stellar mass black hole can be in a binary. A primordial black hole, if it exists, could be in a binary too. A direct collapse seed would be massive and early. A quantum black hole would be tiny and short-lived, if it exists at all. So black holes are not a simple set of boxes. They are a network of traits. Now, let's revisit each of the main types you requested, but with a deeper, more story-like description, the kind that feels steady in the mind. Because the goal here is not to race through facts. The goal is to let the universe feel understandable. Stellar mass black holes again, but closer. How they live in binaries and clusters. A stellar mass black hole often spends its life in one of three states. It can be isolated, drifting through the galaxy, almost impossible to detect unless it passes in front of a background star and causes gravitational microlensing. It can be in a binary with a normal star, pulling gas from it, shining in X-rays, and producing time-variable signals. Or it can be in a dense cluster environment where it interacts gravitationally with many objects, sometimes forming temporary pairs, sometimes being kicked out, sometimes merging. X-ray binaries are a particularly vivid case. A black hole orbits a star. The star's outer atmosphere can spill toward the black hole. The gas forms a disk. The disk heats up. The system shines in X-rays. Sometimes it flares. Sometimes it goes quiet. Sometimes jets appear. This is not the black hole doing something malicious. It is gravity doing what it always does, given a supply of material. And these systems can teach us about accretion physics, which is relevant across scales, from stellar black holes to supermassive black holes. The same general principles: disk formation, turbulence, magnetic fields appear again and again, scaled by mass. In clusters, stellar mass black holes may merge, and the resulting gravitational wave recoil can kick the remnant out of the cluster. This affects whether clusters can build up intermediate mass black holes. So stellar mass black holes are not only endpoints. They can be building blocks, small stones that, under the right conditions, can pile up into larger structures. That's a central theme of the black hole story. Growth. Intermediate mass black holes again, but deeper. Why? They are hard to prove. Imagine trying to detect a quiet intermediate mass black hole in a star cluster. You cannot see it directly. You can only observe the motions of stars. If stars near the center move faster than expected, that suggests additional mass. But clusters also contain many unseen objects: white dwarfs, neutron stars, stellar mass black holes. The distribution of these remnants can mimic some of the dynamical signals of a central IMBH. So astronomers must disentangle competing explanations. This is why IMBH claims are often cautious. And it's why progress can be slow. But slow does not mean stagnant. As telescopes improve, we can resolve more stars, measure velocities better, and model cluster dynamics more realistically. In dwarf galaxies, detecting an intermediate mass black hole can involve searching for faint active galactic nucleus signatures or measuring gas and stellar motions near the center. Some dwarf galaxies show evidence of central black holes, suggesting that black holes in the intermediate regime may be more common than once thought. If so, then black holes are not exclusive to large galaxies. They may be a general feature of galaxy formation. That would be a profound shift in our understanding of cosmic structure. And it would strengthen the case that the universe builds black holes early and often, letting them grow alongside galaxies. Supermassive black holes again, but deeper. Co-evolution with galaxies. Supermassive black holes are woven into galaxy evolution. There are empirical correlations between the mass of a galaxy's central black hole and properties of the galaxy's bulge, like bulge mass or stellar velocity dispersion. These correlations do not necessarily imply direct causation in a simple sense, but they suggest that black hole growth and galaxy growth are linked. One plausible connection is feedback. As a supermassive black hole accretes, it releases energy. That energy can heat the surrounding gas or drive winds that remove gas from the central region. If gas is removed or heated, star formation can be suppressed. This can help regulate the growth of the galaxy and the black hole together. In galaxy clusters, jets from supermassive black holes can inflate bubbles in hot gas, preventing it from cooling too quickly and forming stars. So, a black hole, despite being a small region compared to a galaxy, can influence enormous volumes. That's not magic. It's energy output. Accretion can be extremely efficient at converting mass into radiation, more efficient than nuclear fusion in stars. So supermassive black holes, when active, can be among the most energetic engines in the universe. And yet, most of the time, many are quiet. They sit in galactic centers like deep wells, waiting for gas to wander in. Their influence is always present gravitationally. Their brightness comes and goes with feeding. This variability reminds us that the universe is not static. Even giants have seasons. Primordial black holes again, but deeper. Constraints, hints, and the careful search. The primordial black hole idea is attractive because it uses the early universe as a black hole factory, but it is tightly constrained by observations. Microlensing surveys look for transient brightening of background stars caused by compact objects passing in front. If there were many PBHs in certain mass ranges, we would expect more microlensing events than observed. The cosmic microwave background can be affected by energy injection from accreting PBHs in the early universe, providing constraints. Gamma-ray backgrounds can constrain evaporation signatures from small PBHs. Gravitational wave merger rates can constrain populations of black holes formed in certain ways. All of these pieces squeeze the allowed parameter space. The result is a nuanced view. PBHs are not ruled out entirely, but they are not free to be anything. If they exist, they must exist in ways consistent with a large body of data. This is, again, a calming feature of science. Even the most exotic ideas must negotiate with reality. And as data improves, the negotiation becomes stricter. If PBHs are found, it will be because a signature survives every alternative explanation. If they are not found, the constraints will still teach us about the early universe's structure and the nature of dark matter. Either way, the search is informative. Binary black holes again, but deeper. What the waves tell us about the unseen universe. Gravitational waves are not light. They do not get blocked by dust. They do not scatter the way photons do. They pass through the universe almost unimpeded. This makes them a special messenger. Binary black hole mergers tell us about objects that might otherwise be invisible. They reveal the masses of black holes, their spins, and their distances. They reveal that black holes are common enough and paired often enough to merge within the age of the universe. They reveal that some black holes are heavier than many expected, suggesting formation in low metallicity environments or through hierarchical mergers. They also open the door to new categories. If future detectors observe mergers involving intermediate mass black holes more clearly, that would strengthen the case for that population. If they observe unusual spin alignments or eccentricities, that will inform formation channels. And in the far future, space-based detectors like LISA are expected to observe lower frequency gravitational waves, including mergers involving supermassive black holes and in-spirals of smaller objects into massive ones. That would expand the black hole catalog dramatically. So binary black holes are not only a type, they are a method, a way the universe tells us what exists, even when it emits no light. Quantum black holes again, but deeper. The horizon where theories meet. Quantum black holes are the place where our current map has a fog bank. General relativity describes space-time curvature beautifully at large scales and strong fields. Quantum mechanics describes particles and fields beautifully at small scales. Black holes sit at the intersection. The event horizon raises questions about information, entropy, and the nature of reality. The singularity predicted by classical relativity signals that the theory is incomplete in that regime. Quantum gravity is expected to modify the description. But how? Different approaches offer different answers. Some suggest that the singularity is replaced by a quantum bounce. Some suggest that the horizon has microscopic degrees of freedom that encode information. Some suggest that space-time itself is emergent from deeper quantum structures. These are profound questions, and they are not yet settled. So quantum black holes remain, for now, a conceptual tool, a name for the regime where we expect new physics. They remind us that black holes are not only astrophysical objects, they are also philosophical and theoretical pressure tests. But there is a quiet comfort in that too. It means the universe is still teaching us. Even in 2026, even with all our telescopes and detectors, there are still deep mysteries. That, not the kind of mystery that demands fear, the kind that invites patience. Black holes you can imagine, gently, sizes, horizons, and timescales. To make the different types feel real, it can help to picture scale. A stellar mass black hole of, say, 10 solar masses has an event horizon radius on the order of tens of kilometers. That's about the size of a city, yet it contains the mass of 10 suns. A supermassive black hole of 4 million solar masses, like the one in the Milky Way, has a horizon radius on the order of millions of kilometers, comparable to a few times the Sun's radius. A supermassive black hole of 1 billion solar masses has a horizon radius on the order of billions of kilometers, comparable to the size of the solar system. These are not exact numbers for every case, but they anchor the imagination. The bigger the black hole, the bigger the horizon. The bigger the black hole, the slower the characteristic orbital times near the horizon. This means that variability timescales differ. A stellar mass black hole can change brightness on millisecond timescales. A supermassive black hole's inner disk changes on timescales of minutes to hours to days, depending on mass and details. So mass sets not only size, but rhythm. Each black hole type has its own tempo, and that's fitting for a sleep script, because tonight is about rhythm too. Slow, steady, and deep. Common myths, calmly corrected. Before we close, a few calm corrections help keep the black hole catalog clean. Black holes do not wander around sucking everything in. They follow orbits like other massive objects. To fall in, you must come close, and you must lose enough angular momentum. The event horizon is not a place where gravity suddenly becomes infinite. Outside the horizon, gravity follows predictable rules. You can orbit a black hole the same way you orbit a star if you are far enough away. Black holes are not cosmic trash cans. They are part of cosmic recycling. They influence star formation, galaxy evolution, and the distribution of energy in the universe. And black holes are not everywhere. They are common enough, but not omnipresent. They are specific outcomes of specific conditions. Understanding these points makes the universe feel less haunted and more structured, and structure is restful. A quiet ending. The universe has many ways to make a dark horizon. So, what kinds of black holes exist in the universe? There are stellar mass black holes, born from the collapse of massive stars. There are intermediate mass black holes, the possible missing link population, perhaps built in clusters or found in small galaxies, still being confirmed and mapped. There are supermassive black holes, the giants in galactic centers, shaping galaxies as they feed and flare. There are primordial black holes, hypothetical relics from the early universe, constrained by observation, still searched for with careful methods. There are binary black holes, systems whose slow spirals and sudden mergers let us hear the universe through gravitational waves. And there are quantum black holes, theoretical objects at the edge of known physics, reminders that our story of gravity and reality is still unfinished. The universe is creative, but not arbitrary. It follows laws, and those laws allow multiple pathways to the same strange boundary, an event horizon, a line in space-time where escape stops being an option. If you let this sit gently in your mind, it can feel less like a horror story and more like a natural history. Black holes are not the universe breaking. They are the universe obeying its rules in extreme conditions. And we, small and warm on a quiet planet, have learned to detect them, to measure them, to classify them, to listen to their mergers through the fabric of space-time itself. Tonight, you don't need to hold every detail, just the calm outline. Different masses, different origins, different environments. One underlying idea: gravity, taken seriously. Let that idea fade into the background now, like distant thunder that never arrives. The universe continues its slow work. Stars burn, stars die, galaxies turn. And somewhere in the dark, black holes keep their silent boundaries steady, indifferent, and beautifully real. Sweet dreams.